Okay, so let's go ahead and get started of how we're going to use this idea of trig substitution. So this really came about when we have integrals that look something like this, where we have this integral of the square root of a squared minus x squared dx. And here you should know that a here is just a constant, and I'll write that a is assumed to be a positive constant. So just write that here. So it's just assumed to be a constant. It could be like the number 5 or 10 or whatever it is. But it is a constant where a is greater than 0, so it will be positive here. So the question is, how would we integrate this? So it does kind of become difficult because can I just take the square root of each of these? Is that allowed? No, not when there's addition subtraction, right? So it's not like I can just simplify these. The other problem is I can't really make a very good substitution because here if I let u be like a squared minus x squared, the derivative is going to be a negative 2x, and I don't have another x in the integral that I could use sort of as my du. So that makes it sort of difficult for us to actually do this. If there was another x out front, that I could easily do with substitution if there was another x variable, but that's not what we have. So this isn't going to be quite that easy, and we don't really have a technique then to integrate this. So what we're going to do is make what we call a trig substitution. So I'm going to show you why that might be helpful here. So what we're going to do is we're going to let x be equal to a trig function. So that's why we call it trig substitution. We're going to let it be equal to a trig function. And here I'm just going to choose sine. Later I'll talk about in a minute why we choose certain trig functions, but I'm going to choose it to be a sine of theta. Okay, so I'm going to replace x with a trig substitution, which means I substitute it with a trig function. Now let's see what happens under the square root here when I replace it with a sine of theta. Okay, so I'm going to make this substitution and see what happens under the square root. So let's go ahead and plug that in. What will we have then? A squared minus, if we plug, a squared, right? Don't forget it's squared though, right? So it'll be a squared and sine squared of theta. So if I plug that in, that'll be a squared sine squared of theta. What could I do now to simplify this? Could I do anything? Yeah, what could you factor out? A squared. Yep, so I could factor out a squared, which is why I put an a in there, so I could kind of factor those out. What else could I do now? Yeah, I can bring the a out. What else do we know? What's 1 minus sine squared? Cosine squared. So I'm going to replace this a squared I can now take out, and I'm going to replace this with cosine squared theta. Once I do that, I can take the square root of both of them, right? Because now they're separated by times, they're factors, so now I can take the square root of both of them. So this comes out as a, and a is already positive, we said that. And technically when the cosine comes out, it's just cosine, but it's really, technically it's the absolute value. You want to make sure that it's positive, right? Because you can't put a negative in here, otherwise that would give you an imaginary value. So technically that comes out and it's the absolute value of cosine. Now if this was under the integral, then would I be able to integrate cosine of theta, a cosine of theta? Pretty easily, right? That's easy to integrate. So this type of thing is called trig substitution, where we substitute a trig function that gives us something that's actually fairly easy to integrate. Now you'll notice why I chose sine here, so that I could create this factor of 1 minus sine squared that has an identity of another function squared. So that's some of the reasoning behind why we'll choose certain trig functions, is to create these identities that become another trig function squared, and then you can take the square root. So our goal really here is to make what we call a perfect square. So it makes here, this trig substitution makes what we call a perfect square. They're both then something squared so that we can take their square root. So that's the goal in trig substitution. We substitute in, we get these perfect squares, we can take them out, and then they're easier to integrate. So one thing to keep in mind here is, how is this different than U substitution? Well, it is a bit different. So when we do the substitution like this, what we do is we substitute the new variable is actually a function of the old one. So this new variable is the function. I should write it the opposite way. Sorry about that. Rewrite. I wish I had a pencil, but no. The old variable x is a function of the new variable theta. Okay, so that's actually what's happening here. So our old variable x is now a function of a new variable, which is theta. Okay. So it's kind of the opposite of how u is. Usually u in that one we would make it a function of x, which is the old variable. Now we're making x a function of a new variable, which is theta. So basically what we're doing here is kind of using the substitution rule in reverse. So I'll write that here. Seems like in some ways we're making it more difficult, but it's making it easier to integrate. So we're using the substitution rule in reverse. And I'll give you kind of a picture of that, or inverse substitution you can think of it as. So basically we're taking a function now that's just a function of x, right? So this is just a function f of x of d of x. And what we're doing now is replacing it with something that's in terms of theta. So in here what we're going to do is be putting in a new function, we'll call it g of theta, replacing x with some function of theta. So x has been replaced with g of theta. And when we do this, we're going to have to include its new derivative as well. So we'll have to include a g prime of theta d theta. Okay. So we are kind of making it a function of a new variable theta, and so the dx will actually have to include some sort of differential that includes the derivative with respect to theta. So we'll be doing that. Now, in order to do that, because we're sort of doing inverse substitution, we want to make sure when we do that, that these functions have an inverse function. And does anyone remember the test you would use to test if something has an inverse function? Anyone remember that? What is it? A one-to-one function, right? So it must be an inverse function, or have an inverse function might be a better word here. So it must have an inverse function. And so in order to do that, we want to make sure this function is one-to-one. This function here, the a sine of theta. So that needs to have an inverse function, the x value there. Okay. So it must have an inverse function, and so we must make sure that it is a one-to-one function. And I'll show you here in a minute how we test that. I write one-to-one like that if you like that, or you can. So the theta function really must have an inverse function, so that's the one we kind of test. So this new function, a sine of theta, must have an inverse function, so we want to make sure it's a one-to-one function. And usually we can do that. Not everything starts out as a one-to-one function, but you can always create one by limiting its domain. Maybe you won't take the whole function, but if you only limit a certain part of it, usually you can make sure that it has an inverse. So remember, an inverse means you can switch the x and y, and it's still a function. So switch the x and y values, and it still creates a function when you do that. So we just got to be a bit careful about that. Okay, so what are the techniques we're going to use? Notice in this one I use a sine of theta. This works when we have kind of the form a squared minus x squared, but we're also going to see different forms, a squared plus x squared minus a squared. So I'm going to give you the three basic trig substitutions that we do. So there's kind of three forms we see and what substitutions we make, and I'm also going to talk a little bit about making sure it's one-to-one, how we ensure that's going to be possible here. Okay, so the first one we saw was anytime you have under your integral the square root of a constant minus x squared. When that's the case, we're always going to make this substitution a sine of theta. Remember, a is going to be a number. It will depend on what's in here. And we always use a rather than a squared. So for instance, if this was 25 minus x squared, we would use 5 sine of theta. Or if this was 10 minus x squared, you'd have to use the square root of 10 to be your a. So that depends on what constant is here. To make a perfect square, we kind of already saw what happens there, but I'll remind you again that when we plug this in, we get this a squared minus a squared times sine squared, and then we're able to make a substitution for 1 minus sine squared and make a perfect square. Okay, so that's how we make this perfect square. Kind of saw it in that first one, but that's what's going to happen. Now, here's a piece that I just want to make sure you know is that we have to ensure that this sine function here has an inverse function, because eventually we're going to have to put it back in terms of x. So we want to ensure that has an inverse function. What do you know about the sine graph? Is it a one-to-one function as it is? You guys know what sine looks like? You don't necessarily need to write it, but you know it looks like this, right? Is this going to pass that? Is it going to be a one-to-one function? Do you know what the quick test is? It's a horizontal line test, actually, is how you do it. Vertical line test, if you remember, just tests for a function itself. But to be one-to-one, you have to pass both. So that's not going to pass it, right? So this one, we have to be a little bit careful. The y's are paired with 2 x's. So if I were to switch them, I wouldn't create a function because I have these 2 x's paired with a y. So that would be kind of an issue. So how do we make sure that it is a one-to-one function? So in the sine, what we do is kind of cut it off. What we're going to do is just from the bottom to the top of the hill. If I just chose this piece, is that one-to-one? Yeah, so this one would not be a problem. It would pass that horizontal line test. So does anyone know on the sine function where that goes between? The bottom to the top. Do you know where the top of this hill is at? What pi value? This is 1. I think it's pi over 2. Yep. So remember, this is pi over 2, this is pi, 3 pi over 2, and so on. It finishes by 2 pi. So it actually goes from negative pi over 2 to pi over 2. If I restrict it to those values, it will be a one-to-one function. And when you do the inverse, it will be a function as well. So I'm just going to make a note here that we're going to need to restrict theta to be between negative pi over 2 and pi over 2, just to ensure we have a function when we do the inverse. Okay, so our thetas will be restricted to that. When I do that, it's also helpful over here. Between negative pi over 2 and pi over 2, if you think about the unit circle, that's like the first and fourth quadrants, right? In the first and fourth quadrants, what do we know about cosine values? They're always positive. So I don't need to worry about putting the absolute value on. Like I showed you the first time, I said we have to put the absolute value on. But if we restrict theta to these values, it will automatically be positive. So I don't have to worry about absolute value. So that's the second reason it's nice to have those restrictions. Okay, so that's the first case. We're going to use a sine of theta anytime we're in the square root of a squared minus x squared. Now, the second case is, what if you have under the square root a squared plus x squared? Okay, so plus x squared. Now, if this changes to a plus, I don't think over here that I necessarily want to use sine squared, because there isn't an identity for 1 plus sine squared. There is for 1 minus sine squared. So I want to use a different trig function that does have an identity for 1 plus it squared. Which trig function has an identity for 1 plus it squared? Yeah, cotangent or tangent, right? 1 plus tangent squared, we have an identity for that. That's the one we mostly use. There is for cotangent as well, but we're going to use that one. So we're going to use a tangent of theta. So for this one, we'll use a tangent of theta. And if you make a perfect square on this one, I'll go through that. If you plug that in, you'll get a squared plus a squared tangent squared theta. And what will happen here? We'll factor out the a squared, right? And get 1 plus tangent squared theta. What can we replace 1 plus tangent squared with? Secant squared. So now I can replace that with secant squared, and then I can take the square root of both of those. I've made a perfect square. I can take the square root of both, and I get a secant theta. Technically the absolute value of secant, but I'll show you why we don't need to worry about that either. Let's go back to tangent. What do we know about tangent? Is it a one-to-one function? You know what tangent looks like? Bunch of squiggles, right? Normally we just think of this one, but in fact it keeps going, right? So it has all of these. So if I were to keep all these, it's obviously not going to pass the horizontal line test. So what would I want to restrict the domain to? Probably just one of them, right? If I just use one, it would be fine. So does anyone know where the tangent goes between this one piece? Where does... That's right. Has asymptotes at negative pi over 2, and pi over 2 crosses at 0. So that's what we're going to restrict tangent's domain to be. Now, should I include negative pi over 2 and pi over 2 on this one? No, because they're asymptotes. So it will be strictly less than here. So the domain will be strictly negative pi over 2 is less than theta is less than pi over 2. So you can use any value between there, but not equal to that for your theta values. And what happens then is if we restrict it to these values, that's actually also where secant is positive. It's probably been a while since you did the secant graph. Do you remember what secant looks like? It's like these little parabolas, right? But it's just the reciprocal of the cosine. So if you remember, the cosine looks like this, kind of starts up there at 1, and so on. So if you flip these over, there's secant. So here's secant and here's secant. So if we go between negative pi over 2 and 2, that's this right here, it will be positive. So there's secant between those two values. It's positive, so I don't need to worry about absolute values again. So I'm just giving you some theory about why we can drop those off. Okay, so that's the second scenario. Let's look at the final one here, and that's if we have x squared minus a squared under the square root. Okay, so notice it's kind of similar to number 1, but that x squared is positive, and the constant is negative. So on this one, again, we probably want to factor it out so that we have some sort of value 1, or that value minus 1 is going to have an identity. So the one we're going to use for this one is actually secant, is the one they like to use. There's sometimes more than one option, like this one you can use tangent or cotangent. In this one, there is a couple options, but we're going to go with secant. And let's see why that might help us over here if we plug it in. So if I use a secant of theta, I will get underneath here, let's see, a secant squared theta minus a squared secant squared minus a squared. Factor out the a squared, and you'll get secant squared theta minus 1. What's secant squared minus 1 equal to? Tangent. Yeah, I go back to the tangent. So that will give us the tangent squared. And then we can simplify that to a tangent theta. Technically, it should have absolute values, but we're going to look at the domain restrictions here and see why that we don't need to put those on. So I actually just did the secant right here. So here's the secant. It has all these kind of up and down parabolas. So if I keep all of them, of course, those are going to be an issue. So if I do a horizontal line test, it would fail. So I can only keep pieces of this graph. So it actually sometimes depends what piece you want to keep, but we want to kind of make sure that tangent is going to be positive here so I don't have to worry about absolute values. So here's the pieces we're going to keep. So we're going to keep this little piece from 0 to pi over 2. So let's write that one down. So from 0 to pi over 2, and notice 0, it does have a point, but not at pi over 2. So pi over 2 actually has an asymptote here. So we're going to go from 0, including 0, to pi over 2, but not including that. And then the other piece we're going to use is actually this little piece down here. So this one right here to here. Okay, so I'm going to circle those two pieces are the ones we're going to use. If we just use those two, Nice thing is it passes the horizontal line test. This one starts at pi and goes to pi over 2 is where that asymptote is. So the other piece we're going to keep is from pi, that one has a point, right, to 3 pi over 2, which has an asymptote. Okay. So we're going to keep those two pieces. So from 0 to pi over 2, and then this goes from pi over 2 to pi. We're going to start at pi and then go to 3 pi over 2 where the other asymptote would be. Okay, so we're just basically using those two pieces to ensure it passes the horizontal line test. And the other nice thing is then this is where the tangent is positive. So I don't need to worry about the absolute value. So that's sometimes why they chose those two pieces. If you remember tangent, just to remind you, tangent, right, has this asymptote at pi over 2. But between 0 and pi over 2, it's positive here. And also between 3 pi over 2, where the other asymptote is, and pi, it will be positive. So that's kind of why I choose those two pieces. That ensures the tangent will be positive there. So I don't have to worry about absolute values. Okay, so that's kind of the reason why we choose those domains. Mainly for you, it's just going to be important to know those are the domains to use for each of the trig substitutions. So that's important to note, and we will make a note of that too when we start doing the substitution so we know what domain we're dealing with there. Okay, so now let's do some trig sub. Let's do some actual problems here. Do the whole integration. The first I was just showing you how to make the perfect squares, but let's try one here. So what you're looking for in your integral is square roots or powers that involve the square root, like 3/2 or 5/2, because those would involve a square root. And that underneath them, they have some sort of constant with an x squared, either plus the x squared or minus the x squared or x squared plus a constant. And so you can see here that's what we have. You can always try substitution first. You can say, well, what if I let u be like what's under the square root is the du there? But in this case, that wouldn't really be the case. I would have to have a negative 2x as the derivative, and it's not really showing up. So we're going to use then trig substitution instead, because I see this square root of a constant minus x squared. So in that form, let's go back and decide what are we going to let x be, right? So we're doing a trig substitution for x. What do we need to use here? Which function? Sine, tangent, or secant? Sine. And we need to put the a in front, right? What is the a here? 2. So this is a squared is 4, so a is going to be 2. So we're going to use 2 sine of theta. The other thing you'll always need to substitute with it is its derivative. The dx needs to be substituted and put in terms of theta. So once you've decided on x, you also need to find dx. So to do that, you just differentiate the right-hand side. What's the derivative to sine? That will be cosine, right? So that's 2 cosine theta, and it's a differential, so I'll have a d theta. Okay, so when I go to substitute x's, I'll also have to substitute a dx. I will also list the restrictions on this one's domain, so I have them listed here, that the theta here for sine has to be between negative pi over 2 and pi over 2. Okay, so do try to list those when you're doing your homework so you remember them as you go on. Okay, so let's go ahead now and do the substitution. And when I'm done, I should have all thetas. I should have no x's left. So the dx on the top is replaced with 2 cosine theta, d theta. Okay, so remember to replace the dx with whatever it is. Now notice down here I have an additional x squared. So whatever the x is, I'll square that and replace the x with that. So if I square this, I should have a 4 sine squared theta right out front. And then under this square root, I will have 4 minus 4 sine squared theta. So everything gets replaced. So that's all thetas. The 2 right here, yeah, that's from this. When we have the square root of 4 minus x squared, the format is that it always is in a squared minus x squared form. So that implies that our a squared is 4. And so a here is that square root, which would be 2. So a squared is the constant, and so whatever the square root of that is, it has to be the value for a. Yep. And basically that ensures those match up and can be factored out. Okay, so now once you do the substitution, here's what you want to do. You want to simplify as much as you can. You want to pull things out of the square root. You want to reduce the fraction, and hopefully get something we can integrate, but we'll see. So we just got finished doing a bunch of trig integration, so hopefully we'll use some of that, but maybe it will even get simpler. So let's see what happens. So I always do the square root first. So you can pull out the 4, right? And then you'll get 1 minus sine squared. What can we replace 1 minus sine squared with? Cosine squared. So I could just simplify this to 4 cosine squared under the square root. Right? You can show that step or just do in your head. Factor out the 4. 1 minus sine squared is cosine squared. And then I can take that out of the square root, right? What's the square root of 4 cosine squared? 2 cosine theta, right? How is that going to help me? Yeah, it cancels with the numerator. So notice 2 cosine theta, 2 cosine theta, I can reduce those out. They're gone. So really, what do I have left here? I see I have a 4th, right? A 4th you could take out front. And what else do I have? Yeah. You have 1 over sine squared. What is that? Cosecant squared, right? So I could rewrite this as the integral of cosecant squared of theta. Do I know how to integrate cosecant squared? Yeah, luckily I do. There's an integral, right? What does it become? Negative cotangent, right? So this one switches signs. It's negative cotangent. So negative 1/4 cotangent of theta plus c. Now, you're tempted to stop here. You're like, that wasn't too bad. I could be done. However, is this kind of the kind of answer we want? Because what was the original integral in terms of? X. And I have it in theta. I'm like, how do I put it in terms of x? Okay. So just like in u substitution, you don't want to leave u here. You don't want to leave it in terms of theta. So now I have to go back and say, well, what's cotangent of theta? Okay. Here's where you get to use the little right triangle trigonometry. So here's how you can figure that out. So when we have x equals 2 sine of theta, I can set up a right triangle. If I divide both sides by 2, that would tell me that sine of theta equals x over 2. Does that make sense so far? Okay. So that means in some sort of triangle, I have a theta, an angle theta, where I know 2 sides of the triangle, right? If you know sine, what do you know the 2 sides are? What over what? Opposite over hypotenuse, right? SOHCAHTOA? You got SOHCAHTOA down, right? So the sine would give me the opposite side over the hypotenuse. Okay, so I'm using the values that I used to make the substitution and setting up a triangle based on that. So now what I need to know, though, is the cotangent of this theta. What sides would I use for cotangent? What's the ratio? Adjacent over opposite, right? Remember TOA, so tangent is opposite over adjacent, so cotangent is adjacent over opposite. Well, I know the opposite. How am I going to find the adjacent side? Pythagorean theorem, that's right. So whatever this side is, you can call it whatever. Maybe I'll call it side A. A squared plus x squared equals 2 squared, right? So a squared is going to be 4 minus x squared. And so that side is actually the square root of 4 minus x squared. So that's that third side. So you can always use the Pythagorean theorem to find the third side. So from this substitution, you'll always be able to know 2 sides and you can find the third. So to go back and put it in terms of x, I create this right triangle for theta. That's the easiest way to do it anyway. So you can use some inverse functions, but the easiest is to just create a right triangle using 2 sides you know, find the third side, and then figure out the ratio for cotangent. So it's negative 1/4. We said it was the adjacent, which would be the square root of 4 minus x squared, over the opposite, which is x. So that's cotangent of theta, is that ratio. now I've got it back in terms of x. And I'm pretty much done. If there's any simplifying you could do with the 1/4, you could do it. Maybe I'll just make it into one fraction here. So negative square root of 4 minus x squared over 4x. And that's it. Okay. So that is trig substitution. Uses a lot of trig. SOHCAHTOA, you're going to have to know that for this one. And all those trig ratios. Okay. So that will be my final answer in terms of x. The integral of that basically came from negative square root of 4 minus x squared over 4x. So once you get down to the final answer here in terms of theta, you always do have to go back and write it in terms of x. So the best way to do that will be to use this equation here to set up a right triangle. Solve for the trig function, set up your two sides and get the third, and then you'll know your trig ratios. What questions do you have right now? Okay, not so far. Let's do another one. See if we can figure out how to set this one up. So let's try the integral of x cubed times the square root of 9 plus x squared. Okay, so again, you might try substitution. Like what could, if u was the inner function, the derivative though would be 2x. And I obviously have a larger value on x here. Exponent is x cubed. So that wouldn't work. If this was just an x out front, I could definitely just do a u substitution. So once I see the square root and I have constants with x squareds, that's where I start thinking trig substitution. So in this form, when it's 9 plus x squared, what do I have to let x be? Tangent. What is my a? 3. So remember, this is a squared. So the square root of that would be 3. So we're going to use 3 tangent theta because it's now a plus x squared. So don't forget you got to find dx because you're going to have to substitute that as well. What's the derivative of the tangent? Secant squared. Yep. So that's 3 secant squared of theta d theta. And I'll list the restrictions for tangent here. This is the one where it's also from negative pi over 2 to pi over 2, but we don't include the endpoints because they're asymptotes. That's right, that's the domain. Okay, so let's go through and substitute all the x's for thetas. Okay, so everything that's an x, you've got to substitute for theta. X cubed, what's x cubed going to give us? 27, and then what? Tangent cubed. That's right, 27 tangent cubed. Okay, under the square root, we'll have 9 plus x squared will be 9 tangent squared. Now, here's the temptation is just to put d theta on there, right? That's the thing I always forget. But what actually goes in for dx? Right, 3 secant squared theta d theta. So now it becomes 3 secant squared theta d theta. Okay. So most common mistake is people forget that dx doesn't just become d theta. It's really this whole expression. All right, let's see if there's anything we can simplify now. Okay, so first under the square root, we can pull out a 9 and then get what? 1 plus tangent squared, right? What will that be replaced with? Yeah, so 9 secant squared theta. And then that will come out as a 3 and a secant, right? Okay, so what do I have all together? Some big number, right? 27, a 3, and a 3. So 27 times 9, what is that? Pretty large, right? 200 something? 243 maybe? 243. Okay, so if I put all the constants together, that gives us a 243 out front. And then I'll have a tangent cubed theta. And what will I have for secants? I'll have secant to the third, right? Secant to the third theta. Now this one wasn't a fraction like the last one where nice things canceled out. So we're going to have to figure out how do I integrate it in this form then if you have tangent cubed and secant cubed. Now we just got done doing that, right? And 7, 2, What's our strategy here? Tangent cube, secant cube. Tangent secant. And then let u be something. Okay, what do we want to try? If you leave a tangent and a secant out, right, you're letting u be secant squared. Is that what you're thinking? Sure. Okay, so let's go ahead and do that. So this would be a tangent squared and a secant squared. And we're going to leave a secant tangent over here as the derivative, for the derivative. If we leave that out as the derivative, what are we trying to let u be? Secant, right? So that its du would be the secant tangent. Alright, so I know this will become u squared. This is our du. What else am I going to have to do? Switch the tangent, right? So that everything is in terms of secant, so that I can replace them with u's. So this can just become 1 minus, secant squared minus 1. That's right? Secant squared minus 1. And then we can substitute the u's. Okay, so if I replace that with secant squared minus 1, this is secant squared, a secant tangent. What is it going to look like when we put these u's in? Who can do it? Anyone want to try? U squared minus 1, good. Then what? This u squared, and all of this is du. Yeah, now we're to u's. First we did thetas, now we're at u's. Okay. Alright, so that's right. So this will be u squared minus 1, a u squared, and a du. And then I should be able to integrate. So not only am I using trig substitution, now I've got to use a technique from the last section where I do a u substitution, but hopefully now we can integrate. So distribute that out, right? U to the fourth minus u squared. And then let's integrate. So what's u to the fourth if I just integrate that? That will be 1/5 u to the fifth minus 1/3 u to the third plus c. Done? Oh no. That's right. We gotta go back to theta first and then to x. Okay, so let's put our u back in. That will give us theta. So what is that? 1/5 secant to the fifth theta minus 1/3 secant to the third theta. Alright, we're getting closer. There's thetas. Now, how am I going to get back to x? What do I need to go do? Up here I need to draw a triangle, right? What do we know if x equals 3 tangent theta? What is the tangent equal to? Yeah, x over 3, right? And that is opposite over adjacent. So use that to create a right triangle. I always make mine like this, but you can make yours however you want. Put in the theta, and you know the opposite and adjacent sides. So you could easily find the hypotenuse, right? What's that hypotenuse going to be? 3 squared plus x squared, and then square root. So yeah, square root of 9 plus x squared. Do you kind of notice that every time the third side matches up to your root up here? Yeah, that always happens. Okay. Okay. All right. So all we really need, though, is the secant ratio. What's the secant's ratio? What over what? So it's the opposite of cosine. What's cosine? Cosine is a over h, right? Adjacent over hypotenuse. So it is, yeah, hypotenuse, which is 9 plus x squared, over adjacent, which is 3. So adjacent over hypotenuse over adjacent. Adjacent over hypotenuse is cosine, so secant is the opposite of that. So then we just plug that in. And if there's any simplifying to do after that, you can, but we'll have a 243, a 1/5. This secant, this entire thing, will be to the 5th power. So that whole square root of 9 plus x squared over 3 will be to the 5th, minus 1/3 times the whole thing to the 3rd. So when I'm done, I go put that ratio in. Got that plus c on there. And then if I can, I would do some simplifying. There's some things that would probably cancel out here. Because 243, what is that? 3 to the something. Is that 3 to the 5th? Yeah, so this is the same as 3 to the 5th. So those will actually cancel if you distribute that in. So this 243 will cancel with 3 to the 5th. And so basically you could write this as 9 plus x squared to the 5/2 over 5. So remember, you have the square root to the 5th. You could write that as the 5/2. The 3 to the 5th and the 243 cancel. Same thing over here. 3 cubed is 27 times 3 is 81. I think that reduces out as well. Does that reduce to a 3 or something? 243 over 81? I think so. Yep, that one becomes a 3. So when I distribute that in, that all reduces and just left with a 3 times 9 plus x squared, this time to the 3/2. So there is a bit of simplifying I could do on that one. Because 243 is different powers of 3, so I can reduce those out. And like I said, when you have square roots to a power, you can leave it in that form. Or sometimes if you want to kind of rewrite a little neater, it's just the 5/2 power, and this one will be the 3/2 power. So that's it simplified. Oh, that's fun stuff, right? This one? Yeah, I would like to see some simplifying if possible. Like if you see like 27 and this is a 3, like you should be reducing those out if you can. So, yeah. Reducing if you can. It doesn't matter to me the format of square roots with powers or 5/2. Either one of those is okay. Okay. Yeah, so remember, what's the power of when you have a square root? What is that power the same as? 1/2, right? So I just took the 5 times the 1/2 and made it 5/2. So same thing here. This is a 1/2 power. You times it by 3 and you get 3/2. That's just a different form, but they're both acceptable. So, okay, is that good stuff right there? I think that might be all for your brains today. Does that sound good for now? Okay. We'll do some more tomorrow. I'll do one with some limits. It's the same thing with limits. When you're done, you can actually change limits, which is kind of nice on these because then you don't have to go back to x. You can avoid the triangle. I better double check and make sure the homework assignment doesn't have any of those first. But you can get out your homework and we'll see if there's a couple questions you want to go over before we quit today. Does anyone have a copy of the assignment? I can't remember what numbers it was.
It was 22.
Yeah, I think you got it. Numbers at the top? Oh, anyone have it for the 7.3 one? Do you have it written out? Okay, tell me which ones. Oh, you got it? Thank you. Alright, so 2 should be fine.
And then all that over 1.
8. Yeah. Perfect. Okay. All of those you should be able to do. There's actually only 4 problems, so those will just kind of get you started for now. So, yeah, all the part 1 numbers should be good to go. None of them have limits, so next time we'll look at the ones with limits. Okay, so the attendance is coming around. Just make sure you sign that. What? Any problems from 7.2, part 2? Should look at. Anything there? Yeah, Nathan? 57. Okay. Okay. The area bounded by the given curves. This one, sometimes it might be helpful to just graph it on your calculator to see what's going on here. This one was kind of fun to look at from 0 to pi. So on this one, when I graphed it, I'm probably not doing this justice, but I made the window from 0 to pi. And you can graph it on Graphmatica or something like that. But when I did, let me show you what it looked like here. One was kind of on top and one was slightly underneath. So from 0 to pi, it kind of looked like this. Like there's this one that was kind of going up and down. And then the other one was kind of right below it, but just a little bit below it. And it kind of actually met up in the top and then a little bit below that. So when they say the area bounded by the curves, it's the area between them right here and here. So this is also kind of a Calc 1 thing. So they kind of meet at the top. The top function was actually the sine squared, if I remember right. And the bottom one was the the sine cubed. Okay. So anyone know how to set this up if you want to find the area between them? You integrate from 0 to pi, right? Those intervals. And what do you have to do? Yeah, you take basically the top function, whatever that function is, minus this one. Because if you integrate this, it will give you all the area underneath it. And then basically you subtract off the area under this one, and it will give you the area in between. So yeah, you take the top function minus the bottom function. So basically you're taking all the area under the top one and subtracting the area that's under the bottom one. And that way you only have what's left is in between. So yeah, so integrate this. Let's see, any way we could integrate this? I split them up into two pieces. Is that what you guys did? That was probably the easiest. Like sine squared, you can just use power reducing. So that's like 1 minus cosine of 2x. And then I did a separate integral for sine cubed. What did I do with sine cubed? I think I split it up to sine and sine squared, right? And then you can do a u substitution. So that's probably the best one to do here. So make it sine squared and then sine. And then replace that with 1 minus cosine squared. And I did a u substitution there. I don't know if that was the easiest or not, but that's what I did. Did it? Okay, good. So this isn't hard to integrate as it is. And then this one, you could replace with 1 minus cosine squared, and then let u be cosine, yep, and du, it would be the negative sign. So let's see what we end up with if you get the right answer here. So when I integrate this one, let's see, I get 1/2 x minus 1/4 sine of 2x. And I'd evaluate that from 0 to pi. This one at cosine, you could also change the limits. I don't know, did you change the limits on that one or kept the 0 to pi? Did you change them? Yeah, so if you change the 0 and the pi, the u will become 1 and negative 1. So this will be minus the integral from 1 to negative 1, 1 minus u squared du. And I think that will change it to a plus because I got this negative out front and this negative here. So this one should give you 1/2 pi. Oops. 1/2 pi. And this will be minus, sine at 2 pi is 0. Minus, both of those are also 0. So out of the first one, you should just get 1/2 pi. This one, if you integrate, you get u minus 1/3 u cubed, and you plug in 1 to negative 1. And you do have to do that order, which seems weird, but that's the order they were given in. So I have 1/2 pi here. This one, let's see, will give me negative 1 plus 1/3 minus 1 minus 1/3. Yeah, negative 2/3 and another negative 2/3, so minus 4/3. So that's the final answer on that one. So this is negative 2/3 and another 2/3 subtracted, that makes negative 4/3. So that's how I did it. Split it up, then integrate the pieces. Okay, any other questions? D7, that's the, oh, Wait, I kind of wrote that wrong, huh? Sorry, that's not down with the 2. It's just 1/2 pi. There we go. I don't know why I put it down with the 2, but it's 1/2 pi is what that should be. Anything else? What question? Uh-huh. Mm-hmm. G of theta. Mm-hmm. Yeah. Kind of, yeah. Because normally what we do in substitution is we don't put things back in. So normally, I'll write it like this. In substitution, what we do is take something that's already in that form and replace them with u's and du's. So what happens then is when we're done, we actually get something simpler. That's f of u du is substitution. So in substitution, we take this and make it this. So that's what substitution is. And d theta. Just a messy notation. So this is what substitution does, is this direction, u substitution. In trig substitution, we go backwards. So we take something that's taking f of x dx, and we go back and put it into that form. So we're now kind of making it a bit more complicated because now we're putting in thetas and derivatives with d theta. So that's why I mean it's the reverse of u substitution, is to go back and actually put it into terms of thetas, making it actually a little more complicated. More stuff is in there. So yeah, that's what I meant. Does that make a little more sense now that you kind of see the directions we're going? Yeah, so that's kind of what we're doing, is kind of the opposite of that. Yeah. Yeah, so that's why inverse functions and those types of things are important. So, yeah.